Hey everyone, today we are going to build a dog breed classification model using deep learning. We'll train a powerful model that can look at a dog's picture and predict its breed. We'll go step by step, right from downloading the dataset to setting up our project in Google Colab, and explain every line so you can code along. Let's dive in. The first step is to collect the dataset. Just click the link in the description and download it. To maintain proper folder structure, create a dedicated folder in Google Drive named dog underscore breed underscore project. Inside that, place the dataset and rename it to clean underscore dogs underscore dataset for clarity. Wide drive because large datasets don't fit in Colab temporary storage and drive makes the files persistent. What model are we building? We are building a transfer learning model using MobileNetV2. But what is transfer learning? Transfer learning means we take a model which is already trained on millions of images like dogs, cats, cars, shades, and we reuse that knowledge to train our own smaller model faster and more accurately. MobileNet V2 is lightweight and very fast. It already knows how to detect eyes, ears, texture, fur, shape. We only need to teach it is the final step. Which breed is this dog? That's why we add our own layers on top. Let's jump into Google Colab now. First, we mount Google Drive so Colab can access our dataset and save models. After running, Colab will prompt you to authorize. Once authorized, your Drive files becomes accessible from the notebook. Next, I list the project folder so viewers can see, yeah, we have the dataset. Next, list the dataset. It will show you all the subfolders inside the clean docs dataset. Each of these folders will contain the images related to that breed. Okay. Next, install. Install packages. Pip. What's pip? Pip is a Python's package manager. Install TensorFlow. TensorFlow is a deep learning framework. It is used for building, training, deploying neural networks. NumPy, it is an essential numerical computing library. It's used for arrays, matrices, and for fast mathematical operations. Matplotlib, the most common plotting or visualization library. You will use it for showing sample dog images, plotting model accuracy, loss graphs, etc. Next, define base paths. First, you import Python's built-in OS model. It allows you to work with folders, file paths, creating directories, moving files, checking whether a file exists or not. Then, base directory. It is the location of the main data set. Okay. Then, train directory. You are defining a path for future training dataset folder. Later, you will probably split your data set and save training images here. Okay. Validation directory. You are defining a folder path for validation dataset. Validation images are used to check the model's performance during training. Okay. Next, install split folders. Why? Because this library is used to automatically split a dataset into train and val folders. Okay. Let's look at the parameters. Base directory. It's the source folder. Output is the folder where new train or val folders will appear. Seed 42. This will ensure the split is always the same every time you run it. Okay, ratio is 80% goes to train and 80% goes to validation. Now we create the generators. Import image data generator. It automatically loads images, resizes, augments, scales them. Okay, image size is 224. Why? Because this is the required input size for MobileNetV2, and all the images will be resized to 224. Batch size is 32. Model will process 32 images at a time. Okay, these why do we need to need generators? Generators helps model learn better by modifying images, like such as, see, rescale, convert pixels 0 to 25 to 0 to 1. Rotation range is 20. Randomly rotate images up to 20 degrees. Some random translations, slant images, zoom in out, then flip images horizontally, fill empty areas after shift or rotation. Okay, this prevents overfitting and improves accuracy, makes your model stronger and more general. Val data generator only scales images, no augmentation, because the model is tested on the real unmodified data. TrainGen reads images from the train folder, resizes all the images to 224, uses batch size 32, and the class mode is categorical. Why? Because multi-class dog splits. Same for Valgen also. Next, cleaning the corrupted images. From PIL, import image. Image library is for reading. With image, we can open and verify images. Okay. Next is the function, clean dataset. Here we have a counter removed is equal to 0. Counter to track how many images were deleted, and loop through each breed folder, build the full path, loop through every image in the each breed folder, build the full image path, try to open and verify image. If the image is corrupted, verify will throw an error. If the image is bad, delete it and print the file name. So run this function for both train and validation. Val. Okay. Next, we also remove very blurry or unreadable images using OpenCV. Here we import CV2 for image processing to check blurriness. PIL image, we know, test if image opens correctly or not. NumPy for numerical operations. TQDM shows progress bar during checking. This function checks if an image is blurry. Read an image. If the image cannot be read, treat it as bad. Then convert it to grayscale. Use Laplacian variance. If high variance, it is sharp. If low variance, it's blurry. If the variance is below threshold, it is blurry. Okay. Next, clean dataset function. It iterates and deletes blurry, corrupt images. TQDM shows the progress bar. How it actually runs, let's see. Cleans every breed folder, loops through each image, shows the progress bar, check blurry images, running on both train and value. Okay, yeah, see progress bars. Now build model using MobileNetV2. First, load the MobileNetV2 trained on 1.2 million images. Okay, remove top layer. So you can add your layers. Okay, input is 224 into 224 images with 3 colors. Base model dot trainable is false. Freeze base layers, they won't be updated during initial training, so training will be fast and uses transfer learning. Now add your custom layers. This will convert the feature maps into a single vector. Dropout 0.4, prevent overfitting by randomly dropping 40% of units during training. Dense 256, here fully connected layer with 256 neurons and ReLU activation is used. Dropout 0.3 for more regularization to prevent overfitting. Next, final multi-class classification layer with softmax. Softmax converts raw outputs into probabilities for each class. Just create a model. Now we'll compile the model with ADAM optimizer, categorical cross entropy. Why? Because it is multi-class classification, and track accuracy. Okay, yeah, we update weights using ADAM optimizer with small steps. 0.001 is small to protect pre-trained weights. We measure errors using categorical cross entropy for multi-class labels. It is appropriate when labels are one hot coded, and you track the accuracy during training and validation. Accuracy is it means percentage of correctly predicted samples. Helpful to monitor if the model is actually learning or not. Next, callbacks. Here we have model checkpoint. It saves the best model based on high accuracy. Early stopping stops training when validation accuracy did not improve for patients' epochs. Here we have 5. And restore the best weights. Okay, now train the model. Main phase, yeah, model fit. It uses training generator. Validation data is equals to validation generator. Evaluates performance after each epoch. Number of passes are 10. Trains for 10 epochs. Okay, 1 epochs, 1 time training. 10 epochs, trains for 10 times. Callbacks saves the best version. Okay, this process usually takes some time because the network is learning from thousands of images, right? When you train it on your system, the time will depend on your GPU or CPU speed. Have patience, it takes some time. Okay, next, after completion of 10 epochs, fine tuning. Okay, base model trainable is true now. Allow updating of base model weights now. Okay, previously you froze the entire MobileNetV2 base to use it as a feature extractor. Now you unfreeze the top 40 layers so the model can fine tune features, especially for dog breeds. Why not all layers? See, lower layers detect general features like edges, textures. Top layers detect complex patterns. Better to adapt them for your specific dataset. Then recompile with smaller learning rate. Okay, you update weights very gently, avoid destroying pre-trained features. Stable fine tuning especially important in transfer learning. callbacks as before, save the best, fine-tuned model, and early stop when validation stops improving. Next, model fit. Here, fine-tune. Runs additional training epochs on the top layers of MobileNetV2. Now the model adapts better to your dog breeds dataset, improving the accuracy. This will also take some time. Have patience. Okay. After fine tuning, save final model. Model.save path saves the model in Keras format. Saved directly to your Google Drive. You can later load model for inference. Actually, what is saved in this? Model architecture, the layers and how they are connected, weights, learned parameters of the model. Optimizer state is also saved, so you can resume training if needed. Check final performance on the validation set. Model evaluate valgen. This will evaluate the performance of your trained model on the validation dataset. Returns two main metrics: val loss, val accuracy. Print formatted results with 4 decimal places. How to stop overfitting? If training accuracy much higher than validation accuracy, model overfit. You can show training versus validation curves to demonstrate. Okay, here is a demo. Upload an image and the model will predict the breed. First, let's upload. This will file upload function will open file picker in Colab, upload a dog photo. Okay. Next, image is for loading and pre-processing images, NumPy for handling arrays, matplotlib for displaying the image here. Import them. See, train gen dot class indices. This is a dictionary mapping breed names to class numbers. Okay. Then load the image and resize it to 224. Convert to NumPy array. Add batch dimension. Here by 255 is to normalize the pixels to 0 and 1. 0 to 1. Model.predict image array. This will return the probability vector for each breed. NP Rmax predict finds the index of the highest probability. Predicted class. That's the predicted class. Okay. Next, map index to the breed name using class labels. Use matplotlib to display the image and prediction. And breed name is also printed. Yeah, it shows the uploaded image. Next, this is the final. Create an index to breed dictionary. This is very useful. Train gen.class indices is a dictionary. We have already discussed. This maps the breed name to class index. Just reverse that dictionary. Index to breed name. And open a file called labels.json in write mode on your Google Drive. JSON dump labels F writes the dictionary to a JSON file. JSON is a lightweight human readable format that can be loaded later to map model outputs to breed names. Our model outputs the indices that should be mapped to the breed names and printed. When you load the model in another script or app, you can read labels.json to translate the prediction indices into actual breed name. Okay. Done. We are done. Yeah, I'll put the notebook in description. Thank you so much for watching. This was my first ML project on the channel, and I hope it helps you learn and build your own models. In the next video, I'll show you how to take this trained model and turn it into a full web app. Thank you.